So today I'm going to talk about managing data on personal devices. And to begin with, I want to talk a little, look at the way we may have done this back in the day. So long before we had cloud storage type things, you may have used point-to-point synchronization to manage personal data. So for example, if you took a mobile device, you went and took some pictures, you could then go home and copy those directly to your desktop or your laptop. And this was easy. It was, you just plug the two devices together, worked nice and fast, and there's nothing complicated here, or almost nothing complicated here. Okay. So if you then add more devices to this, it gets a little bit more complicated. If you have one device that's clearly in charge, you can nominate that device to act as a central hub to store everything. As you produce content, you can then bring those devices back to the central hub, plug them in, and copy everything there. And of course, that works as long as that central hub device is available, as long as it doesn't fail, and as long as it's in the same place as you are. Now, since then, of course, we can take that central hub and replace it with any number of cloud services. So you could say take photos, upload them to the web, and then view them from that centralized, as far as the end user is concerned, that centralized service from whichever other device you happen to be on. This gives you a lot more flexibility over a single hub. Of course, this doesn't work if you don't have a network connection. If you can't talk to the internet, this means you can't view your data collection. And also, if you have a very slow link to the internet, you can also get lots of problems because if the objects in question are very large. So if you then look at some of the ways that people cope with these kinds of problems when they have either poor or intermittent network connectivity, you could do something like take pictures on a local device, and then if you want to copy them either because you have limited space or because you want to make sure you have a redundant copy, you could use some sort of local transport to copy them to another device you have locally, and then later on, when you have a working connection to the internet, upload them to your centralized storage provider. And the problem with doing this is that basically the end user has to pay attention to all the details. They have to set up the local connection. They have to decide where things should go, and they have to remember later on when they're somewhere where they have working network, they have to remember to go ahead and manually push things back to the central store. So the real problem here is there's too much management by the end user to make this a real convenient option in many cases. So to address these kinds of problems, what I'd like to do is propose a property that I'd like storage systems to have. I'm going to give this a name. I'm going to call it device transparent storage. And the way I'd like it to work is as follows. Say I have a collection of devices, all of which are mine in some sense. If I look at the content which I can see from that one device, and then go and look at what content I can see by looking at any of my other devices, I'd like to see the same collection. And along with just seeing that the same collection exists, if I make a change on one device, say I take a new photo, and then go look at what objects I can see on the other devices, I'd like to see that same change appear there as well. So to summarize, this property of device transparency means that I'd like to have the same global view of my data collection regardless of which device I'm looking at. I'd like that property to be true. Now, of course, you can then immediately ask, well, is this impossible in practice? Because there's a number of problems that I alluded to earlier. Namely, devices can have limited local storage capacity. So for example, I haven't yet met the phone or camera that could store all the pictures I've ever taken. And that's been true for quite a while. And then similarly, if I have network connectivity that's intermittent, that means I can't rely on getting at data that's stored on a remote device. So the question is, well, can I provide something that's actually useful in a device transparent storage system, even in the face of these two challenges? And that's what I'm going to discuss for the rest of this talk. So one approach that we can take is to look at the kinds of objects that we're storing here and split them in half. We can split them into the metadata that describes what the objects are, and then the content, which is the actual bits that compose the picture, the music, the email, etc. The metadata has this nice property that it's very small in comparison to the total object size. So that means that I can afford to copy it to all of my devices. On the other hand, the content itself can be very large in comparison. It's not small in general, and I'll only be able to place it where it's actually needed. So to continue on this, it's worth pointing out that there are cases where the metadata itself is useful alone, even if we don't have the resulting content. So if you consider music files, for example, if I'm disconnected from the internet and I don't have the content stored locally, but I have the metadata, there's still a number of things that I can do with the objects. I can enumerate what all these songs that I have. I can view which songs are in which collection, so I can edit playlists or look at what things I've liked or disliked and so on. I can move objects between collections. I can edit the metadata at that point. And I could also maybe do things like identify which content does have the object I want. So if it turns out that it's a device that's turned off or is actually available locally, I would know where to go and get it. Okay, so we need to add two more pieces to make this work into a useful system. So as I said before, we need to separate metadata from content. We also need two more pieces. We need a peer-to-peer continuous synchronization method, which will provide us the approximation of this device transparent storage system, and this will proceed as fast as network connectivity permits. And for those times when we make changes from a disconnected device, we need a way of automating conflict resolution as much as possible so that we'll end up with an eventually consistent metadata collection. So we took these approaches in a system called EO, and it works from a high-level overview. It works as follows. There's an EO daemon that sits on each device, and it acts as a local storage system. So it sits between the applications running on a particular device and whatever local storage that device has. The devices, EO uses an overlay network that we built as part of prior work to communicate between the devices of a particular user. And this is the system that we built is really meant for personal data and device collections. So we're considering things like music, like videos, like photographs, like email. Like we're not considering things like collaboratively editing presentation slides that we'll then use here. Though you could store them. But that's not the case that we're optimizing for. Okay, so EO has a new API. It does not use the traditional POSIX file system API or any of the other standard ones, and it does this because it has a couple challenges to address. The one that I mentioned earlier is this automated conflict resolution, which I'll come back to. It also has a number of other properties. It makes the version history of each object exposes this as a first-class primitive that the applications can both view and manipulate. And it makes this split between metadata and content explicit so that the applications think of these two kinds of data separately. And it provides mechanisms for applications to describe the placement policy, so which objects should be stored on which devices. And I should note that the properties of this API borrows a lot from lots of existing work. Okay, so here's how EOS fits in between the applications and between the applications running on a particular device. So within the core of the application, it basically has two kinds of operations that the application uses to interact with EO. There are operations that interact with object content, and you can think of this as basically a put and get interface. You create a new object, you put it into the content store, and then you retrieve it later based on some identifier. And separately, there are queries that the applications use over the metadata, and finally notifications that arise as in response to both operations from other applications on the same device and from other devices across the network. There's no naming hierarchy here. It's a flat collection of objects as far as the applications are concerned. And the way that applications identify objects is via this query mechanism. So they search for things based on attributes that they've created earlier or that are common for the kind of data in question. So EO is in complete control of all the network transfers between devices. It keeps track of which other devices are part of the same user and notifies the applications via this notification mechanism when new data items that they're interested in are either created or become available locally. So next I'll briefly describe the content store and the metadata store in a little bit more detail, but though not too much detail. So the content store is very simple. It's basically content addressed block storage, so that applications can add a chunk of data, and they get an immutable identifier that's held as long as that content is kept the same. So this matches the kind of use that we expect. If you think about all these kinds of objects, they tend to be written once and read thereafter many times. So you'll add a piece of music or take a video or take a photograph, then you'll edit the metadata, but generally not edit the content after that. A particular device will hold some subset of the content that's stored across all the devices, and this is guided by the placement rules that applications describe. Okay, so the metadata, on the other hand, is everything that the application and the end user need to identify what objects they're using. So if you think about songs, this would be everything that shows up that you use to filter what thing it is you actually want to listen to. If you think about photographs, this could be the tags that you've applied. It may or may not include things like thumbnail versions of images, depending on how you choose to create the system. And what EO does with this is it replicates it to all of your devices as quickly as it possibly can. So the idea is that this provides this basic property where we see the same collection of objects on all devices. And if you think about this, this is small in comparison to the total size of the objects, which means we can afford to transfer things, to perform frequent synchronizations between different devices as fast as both connectivity allows and as fast as changes occur. Okay, so as I mentioned earlier, we do have a problem of what to do when you perform edits on two disconnected devices that can't communicate with each other. So just to introduce the problem here, let's say you create a file on one device, the camera in this example, you send a copy to two other devices, the network becomes unreachable, and then the phone performs one change, and the laptop in this example performs some other change. So in general, the question is, when connectivity resumes, we can look at the file on some other device, and what should we see there? Whose job is it to resolve this conflict somehow, and what should the end result be? So the way that EO approaches this problem is to track the common ancestors of each file and make this history explicit so that that the applications can look and see this is exactly what happened to this object. So that when applications change the metadata, they explicitly say this is the version that I wanted to replace. So you can compare this to branching in version control systems. It's the same idea. But what this permits is there's a variety of different strategies that you can take at this point. So I'm going to describe briefly a few of them. So for example, you could choose to do nothing. You could treat this as a fork and maintain separate versions thereafter. That's not very interesting. You could arbitrarily decide which version should be the winner based on some sort of intrinsic property of the object itself, like a timestamp. You could let the user pick. You could say, here's two alternatives, and let the user pick. Maybe that would make sense if you actually performed a textual edit of something like a title in two places where it's unclear what the right answer ought to be. If you want to do something like that, what the application would do is create a new version which says it replaces both existing conflicting versions. But what's most interesting is if we can let the applications perform these kinds of operations automatically, and that's really what we'd like to hope happens most of the time. And this is possible because the applications are really the things that have knowledge about what the metadata means and whether it's both safe and a good idea to perform these merges automatically. So if we consider a media player, for example, if one of the things that they track is a play count, and you play a song in two places, it's obviously what you'd like to have happen is you'd like the effect of both changes to occur. And the media player knows that it's safe to replace the two different versions with just the sum of the total. Alternatively, if you say adding a tag to a photo, if you added tags in two different places, the photo editor knows that it's safe to, that doesn't comprise a change. That really what that comprised was adding two different things in two different places, and the right answer is just to apply both. And in both of these cases, the end user would never be aware that a conflict occurred. Even though if you looked through the version history, you could see that, yeah, there was this concurrent change and we don't know how to order them. In the end result is the end user just sees the final result of having both changes occurred. So to summarize, I just want to describe briefly what applications see from EO. So they see a flat collection of objects. They have an identifier that's basically just an opaque random number. There are as many of these as there are objects that are stored in the system. each one of these objects has some sort of graph of versions that describe how it's evolved over time. And then each one of these versions has application-defined metadata, so a collection of key-value pairs that make sense for those applications and for that kind of data. And one of these metadata components might be a pointer into the content store saying, here's an actual object that may or may not be present on any given device. So there are a number of challenges to implement a system to carry out this API. They can sort of break them down into two pieces. One is, how do we provide the device-to-device connectivity that we need in order to know who and when to transfer things between. And that sort of basically falls under the category of the previous system, the overlay network that we're building upon, which I'm not going to talk about anymore today. The rest of it falls under the category of how do we continuously synchronize these changes as soon as they occur. As soon as we decide that another one of my devices is reachable, what should I send to it in order that we can afford to make this process efficient and make sure that changes appear as soon as possible. So since we have two different kinds of data, we treat them very differently as far as the underlying synchronization goes. So metadata is fast, it's small. We want to send these updates as fast as we can. And the end goal of the metadata synchronization protocol is to produce identical copies of the metadata on every one of my devices. We'll also make use of the metadata to track where content actually resides. Content, on the other hand, is big, could be slow. We'll do that later depending on what the network availability actually is and how much space we have and so on. So I'm only going to briefly describe how the synchronization protocols work. There are more details in the paper, of course. But the basic goal of the metadata synchronization protocol is to quickly identify once we've discovered that a device is reachable, which updates it's missing. And the way we do this is we assign a single version vector to the complete state of a device. We can do this because we know the total set of devices. So we only need one vector to describe the total state of what updates a particular device has seen. And then if we decide that a device is reachable, we can query it for any updates that have occurred since the time we know about, and it'll send any updates which describes the metadata about changes that have occurred since that time. For content, we have a different set of challenges. One challenge that's somewhat unique to our system is that we have to make sure that we pass responsibility for which devices store a given object. Since the applications can write arbitrary rules about where they'd like things to be stored, we don't want to require that those actually be achievable or not. You could say, well, a hint would be that I want to store everything everywhere, but if I don't have enough space to do that, then I want to still ensure that I don't lose any data just because I stored something else there first. Just because a rule says it ought to be there, I don't want to assume that it actually is. And we do this by letting the metadata describe which device promises to hold a copy of a given object at a given point. And this works as assuming that we have no lost or stolen devices. In that case, you need more replication of the objects in question. And the way that the objects are transferred between devices, you could actually use whatever transfer mechanism makes sense. You could just request the whole object, or you could do something more complicated like rsync. It really doesn't matter as far as EO is concerned. So we've implemented this in Python. We've built libraries for Python and C for applications to interact with. And now I want to briefly talk about how we evaluated the system. But the main question I want to address is, what can we do with EO that we couldn't do before? And the way I'm going to explore that is to describe how EO fits into existing applications. So note that I've proposed a new file API, or new storage API. We should see how hard it was to interact with this. And then I'll talk just very briefly about the costs of putting metadata everywhere. So we modified a number of existing applications. These are all open source projects, some media players, email, photo editing, and so on. Then we looked at the scope of changes that were needed in order to make this work. And today I'm going to talk most about the photo editor. So this was Raw Studio was the editor in question that I changed. And after we'd done this, we gained a new ability. So to begin with, this was a standalone application that had no notion that it was in a distributed system at all. It would just interact with local storage. Afterwards, if you make a change to one instance of this, one instance on one device, it will those changes will get propagated as soon as the network permits to all of your devices that are running this. And also, you can do a number of things while you're disconnected, even whether or not you have the complete collection locally. You can browse your collections, you can browse based on tags, you can search for particular images, you can view thumbnail images as long as you have them. And if you happen to have the full-size image, then you can open it up and edit it and do all the normal operations that you expect. So in order to carry this out, it turned out to be not that hard. We changed about 3% of the system in question. I should just point out that you can imagine lots of user interface changes that you'd like to incorporate after you have something like EO. These values just include what it takes to restore the existing functionality using EO as its storage mechanism instead of a local file system. And in all the other applications we looked at, we had to change less than 10% of the application in total. So if you stop and think about this, you might wonder whether that's likely to be true in general. Is it just a function of the applications we looked at, or is it likely to hold true if we looked at more? And I think it's true in general for the kinds of applications that we looked at. And the reason for this is that if we look inside one of these existing applications, they tend to have the split between metadata and content already there. So if you look at what they do internally, they have some mechanism for dealing with content, and they have some mechanism for dealing with metadata. And what they do in practice is they'd stick all this metadata in some sort of database, whether it's flat or relational, something like that. The details differ. But then they would force that all to go through the existing file system API. So if we then transform the application to use EO instead, we've just made this split explicit. So we use the content operations for dealing with content for reads and writes. And for the metadata, we just transform those to use EO's database instead of whatever mechanism they'd use internally. So I'd like to just briefly describe how much it costs to store the metadata. So I looked at, this is just one personal collection. This is a collection of email, music, photos, roughly a decade's worth. And then if you extract the metadata needed to store these things in the applications we looked at, what we end up with is that the amount of metadata is basically determined by the number of objects. And then it's the same regardless of what kind of objects we're looking at. So if you look at the total, if you want to know how much metadata you're going to need to store, that's basically determined by how many objects you have. So in this collection, we have vastly more email messages than anything else because those are very small, and it's sort of the worst case for this kind of system. So as I mentioned before, there's tons of related work in this area. Probably the most two closely related, both in spirit and the kinds of mechanisms that they use are symbiosis and perspective, but we borrow from lots of other kinds of systems as well. So to summarize, I've described this new property that I would like distributed storage systems to have called device transparency, whereby you see the same content in a collection regardless of which one of your devices you look at, provides this ability to manage your collection from any one of your devices regardless of which devices actually store the content itself. Described EO, which is a system that we built with a new storage API with explicit version histories to make this system useful. It uses continuous peer-to-peer synchronization whenever the network permits, and described how it fits in with a few existing applications. Be happy to take your questions.
Aman Kansal, Microsoft Research. You talked about the metadata being defined by the application and provided to the storage API. Mm-hmm. So in most cases, I'll use a different application to open the same file on different devices, like say a music file. On my laptop, I may use media player. On my iPad, I may use some Apple software to do that, right? So how do the semantics of the metadata get shared across applications for the same file?
Right, so if you look at this, for a lot of types of files, there are some agreed upon standards for how the metadata for those objects should be stored. So for example, JPEGs, there's a well-defined set of tags that different applications use. And then there's application-specific ones that you can add to that. Same thing for email. There's agreed-upon header types, and then applications can add their own. Same thing for music. There's the ID3 tags for MP3s, and there are extensions to that. So I believe that the same sort of model should work here. We should get the different applications to agree on what the common subset of the metadata ought to be and what format it makes sense to store that with, but then also permit applications to, because they can add arbitrary prefixes that make it clear that they're using extensions, and that then those won't interfere with each other at all. So I think that's the approach to use going forward.
Thanks.
So to quote briefly, the great thing about standards is that there are so many to choose from.
Yes.
So I was wondering, something along the same lines, like what happens when device transparency hits real devices? Like I can imagine my TiVo recording large format videos, storing them on my iPhone, which has this massive amount of data to play on a tiny screen.
Right, so I've looked at that a little bit in the context of photos, and if you note, for example, I didn't include thumbnails in the metadata type, even though you might think of those as metadata. And what it turned out to make more sense in practice was to have a master object that represents the thing, and then have different objects that represent the content that makes sense on different devices. So, and treat those separately. And that lets you use different rules for describing where they ought to go. So you could have more specific rules that said the things that the iPod can play ought to go on there, but not necessarily the full ones, unless it makes sense to do that because you have extra space and you want to use it as in effect a relay, but you wouldn't want to do that in general probably.
Wait, so it's not completely transparent? The data on the iPod is different than the data on the...
So you can have multiple related objects, and they could have pointers to each other. And then if you produce a transcoded copy of the same thing, you could give it a slightly different name. And this, of course, is going to be application specific, I think, as to what those are called.
Have you considered having classes of objects? I mean, the other thing that occurs to me is that these might have different attributes, and I certainly don't feel the need for syncing those 500 megabytes of email metadata onto my camera.
I've considered having that, but have not done so. But I actually think that in a lot of cases, having the metadata on the camera is not actually such a bad idea. Because if it happens to be a device that you have with you, then I definitely want my metadata stored there, because it might be the first one that discovers connectivity to the rest of the world. If it's off in a drawer somewhere, then it's turned off and it's not going to get the updates for it anyway. So there's definitely a trade-off in terms of how fast updates occur and how much overhead we have for this. But I think that the amount of metadata, I don't expect to grow nearly as fast as the total content size in the future. So I think we've passed a point where it makes sense to devote that extra storage space to metadata.
How do you distinguish explicit user action from unintentional user action? So, for example, I unintentionally delete some critical file on a device, and conveniently that deletion is now synced to all of my devices, so I no longer have a backup to restore from.
So things like deletions are treated as they're treated as log entries, and so once you don't necessarily have to carry out their actions immediately. So there's a whole lot of user interface questions here that I haven't gone into, but what UO actually does is it records an entry that says a deletion request was received, and it can choose to carry it out any time in the future. Now then, if you really want to permanently delete something, then you probably want a different hook for that.
Okay, thank you.
So I wanted to ask a follow-up question to Aman's, which is, for existing formats like JPEG and MP3, it's often the case that the metadata actually is embedded into the content file. And that's valuable when you want to take your content and, say, share it with other users who maybe aren't using the system, or external web services or things like that. How do you imagine dealing with that situation?
So what we do right now is when you import an object that has that metadata already attached, we don't touch it. We extract a second copy of it and use that for both the placement rules and for identifying what it is. But we don't touch the original content. And a lot of that will work fine for a lot of those metadata fields, because a lot of them are created at original creation time. I think the thing that we would want to consider is, if you look at things like user-defined tags, we would want to have an explicit export from EO, which we don't have in the implementation right now. But it would look at what metadata is in the actual object itself, and which ones are in EO store, and what ones does it make sense to include on the object additionally. But we haven't done anything in that regard.
Okay, thanks.
Oh.